So to be forthright, so I was looking at the SLAM list, a 2 months back or so, and I saw that Ben was going to be presenting on some of the performance prediction kind of work, and so I didn't. I wanted to present some of that work that's happening, but I wanted to give you, a different story as well, and let you see MSU, through a different project in addition to the grade penalty work. So I'm going to tell you about another project that I've been working on, and then I will touch on the grade penalty work at the end. So it's coming. It's the big finish. So it's really nice to see some friendly faces in the crowd. Thank you all for coming, for taking time, for coming here to eat lunch. The Create for STEM Institute, just so you know, is a research institute that's devoted to studying teaching and learning in STEM from kindergarten all the way through college. So I've been there about 2 years. And I was hired into a project called the Biology Initiative, which is an internal project focused on improving bio teaching and learning across their many departments and programs. And I'll tell you a little bit about that. I'll tell you a little bit about the bio departments and programs. So I kind of want to set the scene with some data before I get into the MSU project that I'm going to tell you about. So if we look at overall undergraduate enrollment, nationwide, it's increased about 45% over the last decade and a half, and it's actually expected to continue to increase in the next decade or so. And if you break down this undergraduate enrollment by 2-year colleges and 4-year colleges, what you find is that the 4-year undergraduate enrollment rate was actually increased at a higher percentage than this 45%. So it was a 54% increase according to the National Center for Education Statistics over this period. So over the same time frame, there's been quite a high an addition in enrollment pressure at institutions, and perhaps you felt that here at Michigan too. So the story is pretty similar at Michigan State. This is data showing enrollments, undergraduate enrollment over roughly a 15-year period. It increased about 11% to maybe 38,000 students in 2013. So it's not quite as much as the national average, but it's going up. But if we pare down and look just at Michigan State's College of Natural Science, we find that the enrollment increase is very much on par with the national data. So the College of Natural Science at Michigan State encompasses mathematics, physical sciences, so chem, bio, astronomy, things like that. Chem, physics, astronomy, and then the biological sciences, which are many departments and programs. So this increased at a much faster rate overall than the overall university enrollment. There's a related, even though much of the STEM instruction happens in the College of Natural Science at MSU, there's a residential college called Lyman Briggs College, you may be familiar with it, that enrolls students who are interested in having an experience that can bridge the gap between the science and the humanities. So the Lyman Briggs College at MSU offers degrees in, for example, the history, philosophy, and history and philosophy of science, or something like that. And that enrollment in that college, increased about 31% over the same time frame. So all of this just to say that, there has been a huge increase in enrollment pressure at MSU, and that is one of the factors that we need to consider when we're thinking about how to transform teaching and learning in the classroom. So I'll say a little bit that, at many universities, the budget is such that if the enrollment increases in a particular area, then obviously the student credit hours increase there, and then there's funding that proportionately follows that credit hour. And my admittedly extremely limited understanding of MSU's budget structure is that it doesn't follow this type of model at all. So what this means is that over this 10-year period in the College of Natural Science, they had this huge increase in number of students, but commensurate funding increases didn't necessarily follow, and so this created a lot of pressure on the courses because they were having to serve so many new students. Not to mention the fact that the College of Natural Science, as does any introductory science course, offers a huge amount of service to those that are outside of the sciences. And so, the 11% increase at MSU had an impact on the Natural Science College as well. So I want to give you 2 snapshots of how enrollment increases affected our science courses, and then I'll get into the project that I'm going to tell you about. So the first snapshot is just looking at total enrollment in a couple of introductory science classes and how they did or did not increase between, by these three time snapshots between 2003 and 2014. So we're looking at total enrollment here. We're not looking by section. Along the, the different courses I'll explain are, these are our general chemistry sequence. I was gonna write out the names and then it just got too big and I thought I'll just tell you what the names are. So these is our general chemistry sequence. Biosci, BS, nobody thought about that when they were naming it. Biosci 161 and 162 is our cell and molecular course and our organismal course. These, you'll actually see quite a big decrease in the organismal course because these courses were reordered during this time frame. So it used to be that students could take either, neither was a prereq for the other, but then in 2010, 2011, there was a big initiative to make the cell and molecular course a prereq for the second one. And so students who have to take only one bio course will only take 161. So this drop in enrollment is, makes sense. These are two second-tier biology courses. This is a microbiology course and this is a physiology course. And then this is our physics sequence for life sciences students. So in some cases, these increased enrollments came with extra sections of the course. And so the average section size stayed the same. But in a lot of cases, they didn't. So PSL 250, for example, started at, or was at around 400 students. This is just for fall in 2003, and it has had no increase in section size, and it is now bumping up against almost 600 students in a single section. So that's a course that serves, actually majors outside the college. It serves psychology, kinesiology, pre-nursing, and things like that. So just a way to show you how these enrollment pressures are manifesting themselves. So I'm going to show you one other piece of data about these enrollment pressures. So it might look a little complicated, but there's actually a fairly easy trend to see in this graph. So what this graph is showing is data from a second-tier genetics class. It's the canonical, second-tier genetics class that, most if not all bio students have to take. And each bar, or each column is a semester. So we're looking at, this is fall of 03, and then the semesters that follow after, so fall, spring, summer, all the way through. And what we're looking at is the percentage of freshmen, sophomores, juniors, and seniors in the class. And over this 10-year period, you can see, so this is a class where enrollments were not increased over this 10-year period, right? So it makes sense that, as that total enrollment was held constant, we've seen the class level of students shift quite dramatically. And I think this isn't something that was necessarily anticipated or really, it wasn't really acknowledged until we started getting override requests from students who were desperate to get into this class. So it's quite problematic because even though we have a large percentage of seniors taking the class, it's actually still a prereq for some of these other biology classes. So for some students, they're going, they're like screaming. So I wanted to share with you a couple of student comments from their override requests so you can just kind of hear the urgency in their voices. So I have 3. The first one is, I took this course last semester and I received a 1.5. So MSU grades, they don't give letter grades. They give 1.5 to 2.5. Everybody has their thing, right? Okay, this is Michigan State's thing. I need to finish with at least a 2.0 in this course when I graduate in spring 2013 to still be eligible for vet school, which I already applied to at Michigan State University and Iowa State. If I don't get an override for this course, I will automatically be rejected from both vet programs and will not graduate from undergraduate school on time. The second one, this section is one of the only ones that doesn't conflict with my other classes. Section 5 also works. Also of note, I need this class to graduate on time and have been waiting for an opening for months. Please help me. And the third one, which is, well, you'll see. Getting an override into this class would allow me to complete all requirements before I graduate, and it would allow me to graduate on time instead of having to maybe take this course the following summer. I would greatly appreciate an override as soon as possible because when applying for financial aid this past year, I was unable to get the full amount because I was unable to register for this course on time, and so my funds were cut due to not registering for the 12 credit minimum to get the full amount. So the enrollment pressure on these courses is creating all kinds of problems for students. Before we get into instruction, I want to share with you briefly 2 other pieces of context about the MSU situation. The first is that if we just look at the College of Natural Science, about 3/4 of natural science students have a major that's in the biological sciences. with the remaining quarter split roughly equally between mathematics and the physical sciences.
Is that 1 year of students?
This is 1 year. It's a snapshot in fall 2013. But it is roughly, so the percentage of biology students has actually decreased a little bit. So I have in my notes here that in 2008, the percentage was about 80% of biological science students. So it has actually decreased a little bit. The second piece of context is that these biology students are spread, as I've probably mentioned this to everybody because I just think this is so, it's just such a key characteristic of how MSU operates, in biology anyway. The second is that these biology students are spread across 5 departments in green, 4 programs in orange, with yet a 5th program devoted solely to teaching the introductory 2-semester sequence that everybody draws from. And graduate work happens in even more places than this. So I tell you this so that you know that when we're talking about chemistry, when I tell you about this project that we're working on, when we talk about chemistry, we're talking about the Department of Chemistry. And when we talk about physics, we're talking about the Department of Physics. But when we talk about biology, we're talking about this. Okay? So it's a multi-headed, decentralized group of many, many, many faculty and many, many, many students. All right. So I've been offering up all these data about structural issues at MSU because of the way in which we've been thinking about education reforms there. So MSU has multiple education transformation, if you will, projects and initiatives going on right now. There's the AAU project that I'll tell you about. There's the biology initiative that I mentioned. The biology initiative, as I said, is focused on biology, teaching and learning. The AAU project is focused on STEM gateway lecture courses. There's a new HHMI grant for looking at introductory lab courses in the sciences. And then there's there's something from Dow too, but I forget what it is at the moment. But I know it's something introductory STEM. So there's a whole bunch of these different, prongs happening or things going on. But this structure is kind of a common way that we think about all of them. And I have to credit this framework to Joe Krajcik. But in all of these projects and initiatives, what we try to do is attend to the structural issues at hand and the pedagogical issues at hand and the curricular issues at hand. And I think I'm probably preaching to the choir when I say this, but I think that forgetting about or neglecting any one of these 3 elements is going to inhibit the effectiveness of any kind of transformation effort. So it's not to say that all of those projects that I mentioned focus on all of those elements, but that we are aware of them and we consider them as we move through each of these projects. So we understand that, for example, how big your class is going to affect what types of assessments you give to your students. So just to give you a couple examples, we could brainstorm about this as a group, but structural issues are things like, how big is your particular class? Who's teaching the class? Are they male or female? Are your classes offered in the morning? Are they offered in the evening? Do you have TA support? Do you have undergraduate support? And then curricular issues would be things like, does your course follow the curriculum of a corresponding laboratory, or does it not? What do disciplinary societies have to say about what the content should be in your class? And what content do the faculty value? And what content is necessary in a class in order to vertically integrate your curriculum? And then pedagogical issues would be more issues of active learning. How can we give feedback to students in a timely fashion? Who talks in class? If you give a clicker question, who gives the answer? Is it you? Is it a student? Or I should say, is it a student or is it a faculty member? Do the students have an opportunity to talk to one another in your class? So all of these components are important when we're thinking about how to improve a class or a degree program or research experience or what have you. And I would conjecture that they've all come up as you have been addressing issues through the Third Century Initiative projects. Okay, so I'll tell you now about MSU's AAU project. So the Association of American Universities, if anybody is unfamiliar, is a group of R1 research universities. It's an umbrella organization for a group of about 60 Research One universities. It's located in Washington, D.C., and it's basically an advocacy group for higher ed in D.C. So AAU put together something called their STEM Education Initiative, Undergraduate STEM Education Initiative, probably 4 years ago now. and put out a call for project sites to look at institutional transformation efforts, to try to bring about institutional transformation efforts at some different project sites. They selected 8 project sites, one of which is MSU. And just a fun fact, the PI of the project at the national level is Jim Fairweather, who is also at MSU in the Department of Higher Adult Learning and Education, something like that. So he's been, he's both a mentor to the project, but he's also somebody who can see this from a national scale. So the project at MSU is focused on creating a coherent STEM gateway across biochem and physics and math, but nobody really wanted to play in math. I should probably edit that out, but okay. We tried. So our overall goal is to transform instruction, as I said, in intro biochem and physics courses so that they focus on, this is the framework that we're thinking about, scientific practices, cross-cutting concepts, and disciplinary core ideas. So this is a framework that comes out of the National Research Council's K-12 framework on science education. I'll tell you a little bit more about that on the next slide. So how are we going to achieve this goal? Well, we have 3 what I call levers for change. I'll put them up here. The first is what we've been calling disciplinary discussions. So what we've been doing is getting together groups of faculty in the 3 disciplines, each in their own discipline. So one group in chemistry, one in physics, one in bio, a few in bio. And asking them, what are really the core ideas that you want students to have in your course? What do you want students to be able to do? How will you know that they are able to do it? And then how are you going to get them to be able to do that in their class? So these are discussions. The interesting thing about the disciplinary discussions is that the nature of organizational change is such that it has to attend to the microculture of each department. And so these disciplinary discussions, even though I've labeled them in one line, they have a really different feel in each of the different departments. So in bio, it's very attached to this bio initiative. And in chemistry, it's very informal. And in physics, it's been something that's kind of happened under the heading of the undergraduate chair for education in the physics department. So some have been more structured and some have been less structured. And that's something that we had to just accept as a reality of the project, that we have our habits and we have our certain kinds of connections with people, and that's how these things kind of have to take place. At least that's how we're looking at it here. The second lever for change is something called the STEM Alliance, which is basically it's basically an email list of everybody who's involved in STEM education in some way, shape, or form at any point across the university. So there's between 100 and 200 faculty members on this list, and what we do is we get together 3 times a year, and there's a kind of presentation or there's a kind of workshop, and it's just kind of like a home base point for everybody to get together. So it's something, the STEM Alliance is something that brings together people from engineering, people from College of Natural Science, people from the School of Education, and then there's also an enormous agriculture college at MSU. The third lever is something called the STEM Gateway Fellows Program, which is a small group of about 8 faculty who were recruited or who applied and were accepted into this fellows program. It draws, again, from all the STEM disciplines, and there are actually some math and statistics folks in the Gateway Fellows Program. And that's a place where people can try out new things in their class. It's a place where people can garner ideas from each other, and it also comes with a financial reward. So it's some kind of incentive and highlight for education. Our research question is really, how will these 3 levers affect what students are taught, that is curriculum, and how students are taught, that is pedagogy, in these introductory classes of interest? So just kind of a key, when I'm talking about what students are taught throughout the rest of the slides, I'm really talking about what we are interested in terms of curriculum, which are these practices, cross-cutting concepts, and core ideas of the disciplines. And then how students are taught are more of these active learning or feedback kinds of questions. The way that we're going to measure this change is through 2 protocols that we're going to develop. We had to have our own acronyms, so we developed 3D LAP and the 3D LOP. And one of them is on assessment. So we're going to be looking at classroom assessments and how they change, or if they change over time. And then observation, we're going to be looking at classroom instruction, which is what I'm going to tell you more about today. So the three-dimensional learning piece comes from, 1, 2, 3. So that's where that comes from. The AAU project is spearheaded by Melanie Cooper, who just started there about 2 years ago at MSU. She came from Clemson. JT Laverty is a physicist who I work pretty closely with on this classroom instruction side of things. And then Zach Nussbaum is an undergrad. These are all undergraduate students. Zach Nussbaum is an undergrad who has put a lot of work into the data that I'll show you today. So it's a really great interdisciplinary group. You can see Joe Krajcik is there. He's on the project as well. Okay. So as I said, the overall goal of the project is to transform instruction in these intro science courses so that they focus on three-dimensional learning. And I thought I would just give you, these aren't examples. These are all of the practices and cross-cutting concepts. Maybe I should have just given you a couple examples, but these are the basic, signposts of this framework. So scientific practices, they were basically written to try to get away from the term inquiry. So there's been a whole lot of talk, not so much now, but previously, in trying to get inquiry into the classroom, trying to get students to develop and practice like scientists and things like that. But inquiry is a pretty amorphous term and means lots of different things to lots of different people. It has kind of some colloquial usage also. And so part of the goal of writing the framework was to kind of parse out what are the things that, what is meant when we say students should be doing inquiry in a classroom. So things like analyzing and interpreting data, we think they should be constructing explanations, we think they should be doing all of these things that you have to do if you're a scientist doing science. Cross-cutting concepts are concepts that show up again and again in disciplines. So the idea that scale is important in biochem and physics, the idea that structure and function is really important in, again, all of the disciplines. So the K-12 framework, as the name says, was developed for teaching and learning of K-12 science and engineering, but it was developed using the best available research on teaching and learning at that time. And there's every reason to believe that the approach is valid through at least the first 2 years of college. And I was telling some people earlier today that if you look at so there's this framework document, and then the document that came out underneath it is the National Next Generation Science Standards, which are being variously adopted by states around the nation. And if you look at some of the rubrics that they have for the high school level in the NGSS, the Next Generation Science Standards, they set an extremely high bar for what students should be able to do coming out of high school. And when we looked at those, we thought, oh my gosh. We would love everybody to be able to do these kinds of things. Like we want anybody who comes out of a STEM program to be able to do this, and even graduate students. We all thought they were very high level. So the reason I didn't list any core ideas up here is because what we were doing is in those disciplinary discussions that I mentioned, we're asking faculty to say, okay, based on your knowledge of the discipline, based on various national documents that have come out, what do you want the core ideas in this class to be? Do you want them to be evolution? Do you want them to be about how, forces causing change and momentum or something like that? And the idea is that the faculty would come to some kind of shared vision, if you will, around what each of these courses should be about. And importantly, core ideas are not topics. They're not topics. They are ways of learning new ideas in a discipline, and they're ways of generating new ideas. So evolution is a great example. Evolution is essential to the study of biology, and it's required to explain lots of different kinds of biological phenomena. And it provides a way for people to understand new data, for scientists to understand new data. So our 3 levers for change, the disciplinary discussions, the STEM Alliance, and the Gateway Fellows program, align with Charles Henderson's work on facilitating change in STEM instructional practice. So Charles Henderson, he's right down the road. He's at Western. You may know him, you may not. He's a physicist by training, and now he's working more in organizational change. He has this framework for change strategies. And one axis is focusing on individuals versus focusing on environments or organizations. And then the other is thinking about prescribed outcomes versus emergent outcomes. So this is a framework that we have really latched onto for a number of different projects at MSU. And the idea is that so what he did, this paper is a meta-analysis of like, I think it's around 200 studies of change in STEM instruction. And he said, okay, well is this paper about saying, I developed a curriculum and now you should go use it? Or is this paper about, we did a faculty learning community and we had faculty come in and they thought about their own assessments and they said, okay, I'm gonna go change them and I'm gonna go back to my classroom. So, or is it about we instituted a reward structure and we said, now we're going to provide $5,000 extra to anybody who demonstrate, I don't know, something like that, something where, you can see the picture. And then shared vision, which is the idea of the disciplinary discussions, which is getting a group of faculty together to identify a shared common goal for a course or research experience or whatever, and saying, and then that structure, that building the understanding that comes out of that, shared vision is something that can live on because it's not dependent on certain, one person or two people or something like that. So we've mapped on, it wasn't an accident that we developed these particular kinds of levers for the AAU project. I should add also that Henderson's paper says that the change strategies that focus on prescribed outcomes are typically less effective, or, well, his wording is stronger. He says they're not good. Says they're ineffective compared to the other two. So that's why we chose not to do something for disseminating curriculum. So we expect the levers to affect both curriculum, what students are taught and how students are taught. Over the AAU project is a 3-year period, and we realize that affecting institutional change in 3 years is like kind of a tall order. So we're hoping that things will go on after the 3-year period. But at least for now, we're doing measurements in year 1 and then in year 3. Again, today I'll be sharing with you data that focuses on classroom instruction, not on assessments. But if you're interested in hearing about the assessment work, you can always invite Melanie down to tell you about it. So if you're at all familiar with the protocols about inventorying teaching practices, you'll know that there are a whole bunch of them. And there's lots of acronyms. There's RTOP, TDOP, Copis, TPI, and they're like yogurt flavors. There's a lot. So this, of course, begs the question, why are we developing our own? Because, the reason is that all of these existing protocols focus exclusively on how students are taught in the classroom. They focus on issues of active learning. They focus on, how, none of them are about content or curriculum or, anything related to the K-12 framework. So our protocol does both. So to show you an example, we coded a video, we took a video recording of an example MSU class and we coded it with the Copis Protocol. So the Copis Protocol has this procedure where every 2 minutes you code if something is present or absent. So if it happened at any time during that 2-minute interval, you code it as present. So, all of these things are, these are all about how the class is happening, right? Are we doing a clicker question? Are we doing writing? Is the professor walking around? Are they following up with students? Here's another fun fact. In the actual paper, this is called F-up. So, another, I think they just, whatever. So the whole point is that if you look at a Copis profile of a class, it looks great. It looks like tons of stuff is happening. But if you look at the content of what's happening in that class, so this is the same class being coded according to, when we look at practices, cross-cutting concepts, and core ideas, it's basically pretty empty. So you can get a really well-developed and really robust-looking Copis profile by doing a lot of active learning about the minutia of the disciplines. And that is what we are trying to move beyond with this project. So you might ask why we are coding. So this is a continuous timeline. That's how we're coding our videos. You might ask why we are coding videos for how students are taught at all. I mentioned we're doing both. So this is the primary piece that we want to do. We are also coding for how students are taught because we wanted to incorporate some information about that because we anticipated that how we coded some of these items might have been dependent on what was actually happening in the class. So we thought we might have different criteria for someone coding a science practice or for someone teaching a science practice if it was being, if it was a clicker question happening in the class versus a lecture. So essentially we didn't want to exclude the idea that you could teach a science practice through using a lecture. I'll note that we also, sure.
I mean, there's a lot of clicker questions. What were they questions about if there was no content down there? Although you
I don't know. So my colleague JT actually coded this one. It was a physics class, and I think it was about determining the center of mass of items. Well, okay, okay. I won't say anymore. I didn't code it. I didn't code it. Okay. It is very. Go ahead, Gina.
I just had another question because it seems like, I mean, that's fantastic, but it seems like that would take a really deep knowledge of the subject. I was wondering who's doing these observations because you would have to really be able to distinguish between.
Right. So that's one of the reasons we're not doing live observations, because I mean, even in the last, I don't want to tell you how many hours I've sat in a room with that group of people, you know, who are listed there and said, okay, what does it mean to teach this? What does it mean to teach that? And how can you teach it? And you know, all of us have PhDs in the different disciplines, and you know, and many of the members of the group are, you know, still are teaching these courses. And so I think that we've trained the group of undergraduates that I showed. We have trained them to code how students are taught, but we are requiring that the pass through the data where we code for the three-dimensional learning is done by people with PhDs in the discipline. And we also have a structure where we've required every coding to be done by 2 people, and then we look at, you know, how closely did they match. So, yeah, we've argued a lot about this. And I'll also note that, oh, sorry, go ahead, Matt.
Were there sort of norming sessions where
Yes.
so people were discussing what counted for one?
Right, yeah. I have to tell you, so I wanted to, the way the group has been functioning, I mentioned there's this assessment piece and then this classroom observation piece. For much of last year, we were kind of alternating our focus. First, we would focus on assessments, and we focus on instruction. We focus on assessments and instruction. And much of the last 3 or 4 months has been solely focused on assessments. And so I wish I could tell you that I have more, I wish I had more data to share with you about how some more summary data about the practices and concepts and things like that. But unfortunately, I don't, just because of the nature of how the group progressed. So, so yeah. But there certainly were norming sessions, and with this data is all complete for the first year, and that's what I'm going to share with you today. I will note that we added this phenomena code to our, I mean, now we don't know what to call it, 3-dimensional or 4-dimensional, but if any of you have ever worked with Joe, you will remember that he has a tenacious focus on phenomena, and that explaining phenomena is like the absolute core of science education. And so we just kind of couldn't get around it. So we're also coding for phenomena. So phenomena would be something like, you know, if an instructor in a bio class is talking about, well, why is it that parents who have brown eyes can have a child with blue eyes? You know, it's not something that has to be a demonstration, or it's not something that has to be, you know, we have a whole set of rules around it. But the idea is that we want to be able to, we want science classes to be focused on explaining the major phenomena of, you know, of our lives. Okay. So I'll just put up the 6. You saw them on the previous slide, but I'll put up the 6 teaching activities that constitute the how of the protocol. These were based on, you know, all of those numerous acronyms that I mentioned before, and we just collapsed the codes for ease of coding, and because we just, you know, we didn't care about all of the nuance of Copis or all of the nuance of some of these other things. So we have these in basically a hierarchy that's mutually exclusive and complete. So every second of a class is coded as one and only one. First, what we do is we look at the students code for clicker questions. Well, they code it all in one pass. It's not like they're doing clicker questions and then tasks and so forth, but this is the way the hierarchy is. So we look at clicker questions, that's students responding with a personal response instrument, and we say, what we have tried to do, we have tried our best to code in such a way that when we code for a clicker question, we are coding for that clicker question, but including, you know, sometimes there's a minute or 2 or 3 or 4 minutes of introduction, and sometimes there's 1 or 2 or 3 or 4 or 5 minutes at the end that's a wrap-up that you're talking about it, you're discussing, you're going back and forth. And so what we've done, both with clicker questions and with tasks, which are basically clicker questions but no personal response device, what we have tried to do to the best of our ability is create whole units. Because what we want to be able to do, you know, for a future, kind of like a future swing for the fences project, is look at, you know, characterizing clicker questions by themselves across the discipline. So if we just look at clicker questions and we have a whole set of criteria for, you know, what do people say are best practices with clicker questions? Do they happen? Do they not? You know, who talks? Who doesn't? That kind of thing. So that's why we did that. Interaction is basically any kind of back and forth that is happening that between, you know, faculty and instructor that's not part of a task or clicker question. Of course, lecture, instructor-directed presentation of content. Administration is the exam is this day, the exam's at this time, and then miscellaneous is just like the crazy stuff like fire drills, or like there was a video of John Wolfe having like Zorro come to his class here, you know, and like someone at MSU got a pizza delivered to them in class, so that's all miscellaneous. So 2013, 2014 was our baseline year, and we're going to be collecting data again this coming fall. And as much as possible, we collected 3 recordings from every instructor teaching a section of any of these courses in fall 2013. Go ahead, Matt.
I was curious about the mutually exclusive part. And what happens with, is there a distinction between a clicker question that's just clicking the answer and a clicker question that's, okay, turn to your partner, solve this, talk about it, now clicker in, and how does that figure in the fact that it's mutually?
Yeah, that's a great question. That's one of the things that we want to do in kind of the sub-next analysis of clicker questions, because we know that there's lots of, I mean, there are certainly places where, you know, where faculty will say, I mean, some people say click in for attendance, and we have that coded as a clicker question right now, because we had to set the rules somehow. But we do want to do, we have a student on it right now, actually Zach. He's a very good student. He was working on coming up with a whole set of codes, you know, to be able to characterize the clicker questions in a particular way. So were they, what did you say? Were they, you know, were they just clicking in, or was there discussion, and, you know, who gave
Because it seems like you got some of those there. If you could combine some of those, it seems like you got it in there.
Mm-hmm. If you combine them, you mean?
Clicker questions and tasks, or clicker questions and interactions.
They're pretty, they're, well, of course, all of a class is kind of related to itself. So it is a little bit, yeah. Okay, so this is our baseline year, and we collected a bunch of recordings, but because of the nature of educational data, you know, we're going to be collecting data again in 2015, 2016, and I'm pretty sure our whole group is biased and thinks that everything's going to be better, you know, in 2015, 2016, and there's going to be way more science practices and explanation and all this kind of stuff in the classroom. So what we've done is we've sloughed off a third of the videos from this year, and we're going to mix them up with all the videos from year 3, and then code those all at once so that, you know, we can mitigate at least some of our, like, totally inherent bias. You know, this is like reality, like we're just all so human. As I said, all the videos were coded by 2 people, and we had very high % agreement. So 80% of the videos, again, we're just talking about the how section of the protocol, 80% of the videos had 90% agreement or higher between them, and the vast majority of the last 20% had between 80 and 90% agreement. And there was a reconciling process for those who had less than 90%. So the overall distribution, if we look at all 3 of the disciplines together, shows about 2/3 of the time is focused on lecture, and the remaining third is split basically evenly between clicker questions and tasks. And I want to emphasize, I think Melanie would want me to emphasize this, that our group is not necessarily of the opinion that lecturing is like terrible and must be reduced at all costs. There are some things, you know, that students aren't just going to discover for themselves in class. And, you know, she has this line about our greatest scientific discoveries were not made by freshmen, with all due respect to any that are here in the audience, right? I mean, students work very hard, but nobody is discovering relativity in, you know, physics 231. So some things, you know, information transfer is not like the devil. Okay. So these are the 3, this is that same data but broken out by the 3 disciplines. So if you like, you can take a minute and guess which chart corresponds to which discipline. Okay? I will say that we have mostly been considering clicker questions, tasks, and interaction as more student-centered practices, and lecture as a less student-centered kind of practice. But you know, there's nuance to that too. I won't ask you to guess so you don't incriminate yourselves. So bio at MSU is very task focused. Chemistry is doing a lot of lecture and some clicker questions, and then physics has quite a few clicker questions. So I think this is something that we couldn't have anticipated at the outset. At the outset, I think we thought that all the disciplines were pretty much going to look the same. But in reality, like I said for the disciplinary discussions, they're each kind of their own little micro environment, which is really interesting given that biology is so many departments and so many faculty and blah, blah, blah. So I wanted to share with you that, okay, this is a little complicated, but it's not that complicated, but it's just busy. The effects, what this is intended to show is that the effects are not due to like single outlier instructors in the disciplines. So, well, there is one outlier. It's right here. You can pick that out. But rather, each instructor nominally displays a pattern that's fairly similar to other instructors in that discipline. So even though we're looking at, we're looking at 2 different bio classes here, we're looking at 4 different chemistry classes here, and we're looking at 4 different physics classes here. These are each instructor, right? B1, B2, these are all different instructors. And what you can see is that, there's a lot of tasks, the red task, showing up in a lot of the bio classes. It's not, this person is obviously very these are 3 different instructors. These people are obviously very task heavy, but it shows up in all of them except for this person, who probably should be a chemist, but, like how they show up. They might, maybe they're like a biochemist or something, I don't know. This is something that we went, that's very interesting, and we're going to see how that plays out in the next couple of years. So each, it makes more sense to me in chemistry and physics that the instructors are similar to one another, because there's another piece that I'll tell you about. Because chemistry and physics nominally have common finals, common exams, common homework, common da-da-da. Whereas bio, they display this common pattern, but the 4 sections of cell and molecular biology, it's basically like the Wild West. There's no common anything. So instructors can do, whatever they see fit, and there's pros and cons to that. So I think it's really interesting that this shows up. So just to summarize, that's the data that I have so far on the science instruction to show you, but just to summarize, the 3-dimensional learning observation protocol is going to be used eventually to characterize both what and how students are taught. We can use it across science disciplines, and I think it's important to note that we want this, the eventual product to be a framework that other adopters can use but also modify. So in the ways that MSU has taken the we've basically identified our own core ideas that are important for each of the classes. That's a really important key that needs to happen when this protocol goes out and gets published. So it can't just be something, where we write it and then we disseminate it to you and then you go off and nobody uses it and nobody cares about it or even remembers it. We know that Henderson's work says that's a really ineffective change strategy. So we want to leave the tool open to modification, and then of course, provide assistance as we can to others who want to use it. And then, of course, we're going to use it to generate evidence of change. There's my bias right there. Okay, sorry. Generate evidence of change in instructional practice over time. Maybe there will be no change. Sometimes I pipe up and I say that in meetings, and they're kind of like, no. So we'll see. So the last bit that I'm going to tell you about is this grade penalty work that we've been working on through the CIC collaboration. So this is, it's kind of a mini story right now. It's I'm not sure how many of you are familiar with the grade penalty work that Tim has presented. It seems like probably most of you have seen it. So I thought I would just give a brief overview. So the idea is that the idea is to investigate how students perform in introductory classes, large introductory classes, both STEM and non-STEM, relative to their performance in other classes. So you can think about, okay, if I got a grade, if my GPA is 3.5 and I just got a 3.0 in this class, well, that's lower than my overall GPA, and that's what we have termed, for better or worse, we can talk about the language, a grade penalty. And then if you do better in a particular class than you do in all your other classes, we term that a grade bonus. So the basic gist of the work is to understand patterns in how students perform over many classes and over many years, and now over 5 universities. So Michigan's participating, MSU's participating, and then we have 3 other CIC institutions that are really undertaking a concerted effort to say, are the effects that we see reliable across these institutions, or are they not? So this is just an example for the biosci, the cell and molecular class at MSU. So, a student who comes in with a 3.0 GPA can expect to get, if you follow it over, somewhere between a 2 and a 2.5 in biosci 161. So what has been interesting about this work and continues to be interesting about this work is that we find similar patterns at our universities despite, you know, the differences in the students that we serve and despite our geographic differences. So, so that's, you know, why we really want to take this and push it a little bit further. So I have two graphs to show you and then I'll wrap up. So this is data for MSU. I'm sorry, it's a bit hard to see. But on the x-axis, we have grade penalty. So dots over here are classes where there's a grade penalty, and classes over here are classes where there's a grade quote bonus. And then the y-axis is a differential for males and females. So if the grade penalty is higher for males, then it would show up here, because that would be female favored. So females are favored up here, males are favored down here. Here's your cheat sheet down here. Females are favored up here, males are favored down here. And I think it's almost a philosophical question to say, you know, whether or not the distribution along this axis is good or bad, right? I think that you could say some classes are going to be harder, some classes are going to be easier, and that's okay. There's going to, you know, it isn't necessarily true that every class has to center around 0, 0. But what's interesting is that the distribution across males and females showed up at Michigan and showed up at Michigan State in very, very much the same way. So this is really what we're pursuing. So this graph has the disciplines coded by color. And one thing that just popped out to me at MSU is that math, although it typically imposes a GPA penalty, doesn't seem to differentiate that much between males and females. So we have to follow that forward a little bit. And that's not just an effect of there being no females in the classes. There's about 50% female representation, and even higher in a lot of the, you know, some of like the lower level ones. Okay, so this is the last plot I have. So as Tim has shown for Michigan, it gets much more interesting if you color these classes according to lectures, which are in blue, or laboratories, which are in red, and then I coded the combined classes in green. So like, you know, 5-credit lecture lab kinds of classes. So lecture courses typically have a grade penalty, whereas lab courses typically have a grade bonus. That is, students usually typically do better in laboratory courses at MSU than they do in their other courses. And females typically get more of a grade bonus from laboratory classes than males do. So why is that? Is it the assessment method? We don't know. Is it because, you know, there's group work and females love group work and males hate group work? I don't know. And there's, you know, we have to be very careful about how we, about what kinds of conjectures we make about this kind of data. But, you know, at least right now it's a reproducible pattern, and it's, you know, it's something that gets a lot of people to say, oh, like, what is that? What's there? What's underneath that? And so I think there's a potential for a whole lot of some really interesting studies, including some qualitative work that could come out of this too. So again, all of this is still work in progress, but we and, you know, Ben and a lot of other people at these other institutions are working toward hopefully a paper, I shouldn't say hopefully, we will, paper this year on grade penalties and bonuses and how they do or don't compare across the 5 institutions. So with that, I'll wrap up and just say thanks so much for your time, and thanks, you know, to Tim for inviting me. It was a lot of fun.
Questions?
Yeah, I have 2 questions about the observational protocol. One's relatively boring, and I hope the second is more interesting. But the first one being, how did you choose which sections to observe, and how many observations did you make to know that you had a valid and reliable measure of that class?
And how did we choose what?
How did you choose which class meetings? In other words, at what point in the term, and how many of each class did you observe?
So we contacted everybody who was teaching any of the introductory classes and said, can we come into your classroom and film? And we attempted to collect 3 recordings from each of those instructors. Some people said no, and there was a weird kind of thing with the bio initiative where in that fall 13 semester we couldn't get any bio data because there was like, people were trying to protect the project, and you know, it was just, we couldn't get any bio data. But in general, we have at least 2 and more likely 3 for every instructor. But they are random times throughout the semester. So that was kind of just a scheduling thing. Can you go now? Can you go now? Can you go now? But we did space them, you know.
Great, thanks. And then the second question was, I appreciated the simplicity of your observation protocol, which I imagine makes it much easier for the raters.
Yeah.
And sort of taking that a step forward, I'm wondering how granular you think it needs to be, especially for the how students are taught. In other words, is it just a matter of lecture and non-lecture? What are you seeing so far that you see makes a difference?
I think that we actually get pretty good distribution. Well, so are you thinking that there's probably more things buried in the lecture that we're probably not pulling out?
I'm wondering if there's actually fewer. In other words, is it is what makes a difference the proportion of time that someone doesn't spend lecturing?
I don't know. I think that it's actually a pretty good level of granularity for the context that we're in. I think that I'm trying to think. I think that we haven't seen too much of the clicker questions or tasks be things that we say, actually that's really something that should just kind of belong with lecture. I'm not quite getting your question, I think. Can you say it one more time for me, actually?
I think what you're saying is the protocol works well as it is.
It does. I mean, there's I think if anything we could have gone a little bit more granular, because there's a real difference. Like I'll give you an example. One of the lecturers that we see at MSU is somebody who has a whole ton of her time coded as lecture, but she's basically constantly asking the class these little micro questions. Like, she's drawing on the board and she says like, what, what should this be? And they say 3, and then she writes it down 3. And then, I mean, she'll have like 100 of these in the class. And so that's a teaching style that's really, really different from somebody who literally stands up and reads a PDF in the class. And that's something that's not, there's something I didn't quite tell you about in the protocol, and we kind of capture it in that way. We're recording when instructors ask students questions that are like non-rhetorical and are about content. And it's not necessarily something that's an interaction. So that was, the interaction code that I had. So that's a way that we can kind of characterize activity throughout the class. It's kind of like a layer on top of these 6 teaching activities. So I think that's a way that we get a little bit more information out of the data. But yeah. Thanks, everyone.